So as we continue our review of derivatives and our review of basic calculus, the next thing for us to look at is first and second derivatives, both in terms of notation and in terms of their meaning. So that's what we're going to get into and talk about today. But before we get started, let's take a deep breath. And let's begin. So the first thing that I'd like to do in this review video is make sure that we're comfortable with the fact that there are really two different notations for how to take the derivative of something, okay? So when we're talking about the first derivative, right, if you've got a function y equals f of x, you can either talk about the derivative of that thing by calling it dy dx or by calling it f prime of x. There's really no difference between the two of them. They're just different sort of notations for expressing that derivative. When we're talking about the second derivative, then this notation is a little bit stranger. It's d squared y dx squared, or it's f double prime of x. Sometimes people ask, like, why is the squared in that position there? I might make a brief mention of that. Another notation that you'll sometimes see, and you would have seen it in yesterday's review lesson about trig derivatives, when someone just says d dx, it means they're about to tell you something to take the derivative of. So if someone said d dx sine x, we would know that this is cosine x. And so in some sense, we can think about the notation dy dx. This basically means the derivative of y. And we kind of just shorthand notation put the thing we're taking the derivative of up on the top. That's not exactly what's happening, but it may give us a little bit of an understanding of where this notation is coming from. So now let's think about the second derivative, right? With this in mind, we could then think about d squared dx squared as being, this is the thing that's representing taking the second derivative of some y function, and so we would shorthand note that as d squared y dx squared. Now keep in mind, no one is ever going to say what's d squared sine x dx squared. Like no one ever writes this. If someone wanted to say the second derivative of that, they could say d squared dx squared of sine x. And this would sort of be asking us to take the second derivative of this. So the purpose of this slide, of this part here, was really just to sort of remind you that we have these two different notations. One of them is the dy dx notation, and the other one is the f prime or f double prime notation. One more thing I might fit in here really quickly. Once these derivatives start to get high, we don't do like f prime 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 prime. You put the number of derivatives you want to take in parentheses up there. Again, I'm not going into a ton of depth on this because these are things that we learned last year or that we've learned in the past, and we're reviewing them. We're bringing that knowledge back to the front of our minds so that we can start to work more with it. Now, you probably remember that one of the primary uses of the derivative that we learned last year is that the derivative allows us to find the slope of a tangent line at a specific input value. And so I've got this example here that I want us to go through, and if you feel comfortable with how to do these things, I would encourage you to pause the video, do this on your own if you want, sort of check in across each of the separate parts. And if you're really confused or you really need more review, I'm going to go ahead and go through it now. So we're given this function, f of x equals x squared e to the x, and part A asks us to find f of 1, right? So f of 1 would just mean we plug in 1, that's 1 squared e to the 1, that's e, so f of 1 is e. Now what does it mean? Well, it basically means that the function f of x has a point at 1, e. And that means that if we were asked to graph this thing, fine, we would know that there's a point at 1, e. Now part B. Part B on this asks us, okay, compute f prime of 1. And what does this mean? So again, I'd encourage you, pause the video now, think about the fact that this is related to the slope of a tangent line. So the first thing that we would need to do here is we need to compute what is the derivative. What is f prime of x? And to do this derivative, we're going to need to use the product rule. So I do the derivative of the first thing times leave the second thing alone, plus leave the first thing alone times the derivative of the second thing. So there it is. That's f prime of x. Now f prime of 1 just means I plug in 1 in all of these spots. 2 times 1 times e to the 1 plus 1 squared e to the 1. This is all just a really fancy way of saying 3e. And now if we think about what this means, right, this is the first derivative. This is f prime of 1. It means that this is the slope of the line tangent to this graph at x equals 1. In other words, at the point 1, e. Okay, so now part C. Part C of this asks us to use the answers above to write the equation of the line tangent line, at x equals 1. Well, great, we've got a point and we've got a slope. We can just use point-slope form. Y minus y1 equals m times x minus x1. That means I'm going to have y minus e equals 3e times x minus 1. And I can actually do a little bit of work to simplify that, right? I could make this y minus e equals 3ex minus 3e, which means, and then I could add this e over and get y equals 3ex. So this is 3e slope times x, and then minus 2e. Either this answer or this answer are both absolutely acceptable. And part D is really, really quick as well. Often, or maybe not often, sometimes we're asked to find the equation of a line normal to a curve. If this first one gives us the equation of the line tangent to the function, finding the line normal means that at that point, instead of being parallel, we're perpendicular to the direction that the curve is moving. There's a lot of really, really neat applications for that when you get into engineering and science that, again, I'm not going to get into right now. The only difference here is that I need to take that slope. My slope parallel was 3e. That means that my perpendicular slope will be the opposite reciprocal, negative 1 over 3e. So then I just need to take this perpendicular slope, and write the equation of the normal line. So y minus e equals negative 1 over 3e times x minus 1. And again, this is acceptable. We really don't need to go any further than that. So recall, we can certainly use the derivative to find the slope of the line tangent to the curve at that point, and we can use that then to write the equation of a tangent line or the equation of a normal line. But there's more that I can do with the derivative than that, and that's really the thing that we need to talk about and review today. So there is this second, or I don't even want to call it second meaning, there is this deeper meaning of the derivative, where the slope of the tangent line is just a specific interpretation or understanding of the derivative. At its core, this derivative, this dy dx, or this f prime of x, is really the rate of change of y with respect to x. And this may sound complicated to you, but really all this means is that dy dx is really just telling you how fast does y change compared to how fast x changes. So if dy dx is 7, it means, all right, this means that y is growing 7 times faster than x is at this particular value. Okay? If dy dx is a half, it means, okay, y is only growing half as fast as x is. If dy dx is negative 1, it means that they're growing at the same rate, but y is actually going down by just as much as x is going up by. That's what this thing is supposed to be expressing to us. This is really about a rate of change of y, the top variable, compared to x, the bottom variable. So I kind of want to give an example of this, and I hope to not take a long time for this. Suppose that I've got this function, y is cosine x over 6. I want us to find dy dx when x is pi. So to do this, I'm going to take this derivative. So dy dx, you'll notice this is going to be a chain rule because there's a thing that's inside here. The derivative of the outside function is negative sine of leave the inside alone times the derivative of what was inside. And the derivative of that is 1/6. So my derivative of this thing is negative 1/6 sine of x over 6. And now the problem asks me to find out what it is when x is pi. So dy dx when x is pi is negative 1/6 the sine of pi over 6. Well, the sine of pi over 6 is 1/2. So this is negative 1/6 times 1/2. That's negative 1/12. Now remember, dy dx is supposed to represent the rate of change of y with respect to x. So what does this tell you? What does that tell you about how y is growing compared to how x is growing here at pi? Doesn't the negative tell us that y is decreasing? And it's not decreasing very fast. This is very slowly decreasing. It's almost like y is going down by 1 when x goes up by 12. So this is not a very slow decrease. And we can actually sort of see that on the graph here. If I were to graph the function cosine x over 6, y equals cosine of x over 6, this would be 1. And basically this division by 6 is going to stretch this graph by a factor of 6. So instead of this graph finishing itself over here at like 2 pi, this thing's not going to finish itself until like 12 pi. And so this graph is like really, really, really slowly coming down to here, and then really slowly coming back up to here. And so when we plant ourselves right here at like pi over 6, we're looking at this saying, well, yeah, and I get that it's going down, but it's really just barely going down right there. That's a sense of what this thing means. And you can see even as I drew this thing that I started to talk about this in terms of a tangent slope, but I can also think about it as a rate of change, as how much is y changing compared to how much is x changing. With that in mind, I hope that you guys remember from last year that we can often make some general statements about a function based on what we know about its derivative, right? So suppose again that we're working with a function y equals f of x. Now, suppose that dy dx is greater than 0 for some value at a. So dy dx being greater than 0, that means dy dx is positive. When the derivative is positive, we say that our function is increasing at a, at that value. Similarly, I hope you remember from last year, when our derivative is negative, when dy dx is less than 0 at some input value, we say that our function is decreasing at x equals a. Now, I'm gonna try really hard here to not use the word it very much, right? Because very quickly we're gonna be dealing with derivatives, first derivatives, second derivatives, and when you say it can be hard to tell what you're talking about. So I was very precise, I tried to be very precise here. When the derivative is greater than 0, the original function is increasing. When the original function, when the derivative is negative, the original function is decreasing. And finally, if it's ever the case that the derivative is 0, it means the derivative is not positive or negative, which means the function's not increasing or decreasing. That function has what's called a stationary point. In other words, the function has sort of leveled out at x equals a. So we've sort of got these ideas here. I'm going to do 2 quick examples that use these, and I want you to work through them and make sure that you use vocabulary really precisely as you talk about what you're saying here. So in this example, let's determine if the function g of x, which is 3 sine x minus 4 natural log x, is increasing or decreasing at x equals pi. So to determine if the function is increasing or decreasing, I want to look at whether the derivative is positive or whether the derivative is negative. And actually, it's not even going to be at x, right? The place that I want to evaluate these things is actually going to be at pi, because the question asked me about when x is pi. So first, what is g prime of x? Well, the derivative of this would be 3 cosine x minus 4 over x. Okay, great. Now I'm going to take pi and plug it in. G prime of pi is 3 cosine pi minus 4 over pi. Cosine of pi is -1, so this is -3 minus 4 over pi. This is clearly negative. So what does that mean? If the derivative, if g prime is negative, what does that mean about g of x? It should mean that g of x is decreasing at x equals pi. That's how we write that. That's what we say. And notice here that I said g of x is, I didn't say it is decreasing, because like I can't make a big enough deal about this. You, especially on an exam, you really don't want to use the word it. Even if it sounds repetitive to keep saying g of x or g prime of x or whatever it might be, refer to the thing that you're talking about. In this next example that we have, I'm asking you to find stationary points. Find stationary points of this function. Now, you may remember being confused about stationary points and what to do with them. We're going to review that coming up. For now, I'm really just getting us used to some of the notation and the vocabulary again, because we're going to be doing a lot with calculus in the rest of this year. It's not all going to be calculus, but there's a lot that we need to do with it, and so I really want to make sure that we have a strong foundation that we're working on. So stationary points occur when the derivative is 0, and so that means that what we need to do is we need to take the derivative and I need to set that derivative equal to 0. Okay, so my derivative here is 6x plus, oh man, I just realized that should have been 3x cubed. I'll go back and fix that. So this thing here is going to be, let's see here, if this was a 3 up there, so this would be 9x squared plus 30x. Now if I took this and set it equal to 0, I could factor this 3x times 3x plus 10. And so this will give me that either 3x is 0 or 3x plus 10 is 0. And that means that x is 0 is one stationary point. I'm sorry, that's the location of a stationary point. And the other one would be negative 10/3. So since they said find the stationary points, we actually do need to plug those things back in. So I would have 0, 0. I got this other 0 from plugging the 0 into this function. And the other one, if I plugged negative 10/3 back into this, let's see here, that would be 3 times negative 1,000 over 27 plus 15 times 100 over 9. Fortunately, these are going to cancel down to giving me a 9 here. And then this, so this is negative 1,000 over 9 plus 1,500 over 9. So this is negative 10/3, comma, 500 over 9. All right, these two things are the stationary points of this function. Whether these are maxes or mins or saddle points or whatever, we're going to get into that in another lesson. For now, I just want us to remember that we find stationary points by taking the derivative, setting it equal to 0, and then finding the y-coordinate that goes along with that. The next topic for us to remember and come back to in our study of calculus is this idea of the second derivative. So first, remember that there are two different notations for it. There's the d squared y dx squared, or the f double prime. And the key point, the thing I want you to recall to remember, is that this second derivative, the second derivative of y, or the second derivative of f, is really nothing more than the derivative of the first derivative. So if the derivative of f is supposed to tell us about how f is changing, then the second derivative is basically telling us how is the first derivative changing. Is the first derivative increasing or decreasing? Is the first derivative getting bigger, or is the first derivative getting smaller? And as we move into this, it turns out that there's this thing called concavity that's going to be wrapped up in this, right? So we say that a function is concave up at a value if the second derivative is positive there. And we say that a function is concave down at a value if the second derivative of that function is negative. We are going to have more lessons this week this week and next week about concavity and increasing and decreasing functions. So this is something we'll spend more time on. I'm really just trying to bring these ideas back to the front of your mind. So now I want to really try and connect together the original function and the first derivative and the second derivative, and I'm hoping that we can sort of see how all these connect to one another, right? So first of all, recall from about 5 minutes ago, when we say that dy dx is greater than 0, it means that y is increasing compared to what x is. So I want to point out, if we really, really work carefully, we can make some similar statements using higher order derivatives. So remember, if a derivative is greater than 0, it means that the thing that you took the derivative of, that thing is increasing. So if the second derivative of y is greater than 0, it means that the thing that we took the derivative of, in other words, the derivative must be increasing compared to x. Okay? But the second derivative being 0 also means that the function is concave up at that input value. Now, graphically, I hope you guys remember that being concave up effectively means that your graph looks like a smiley face, or it looks like one part of a smiley face or the other part of a smiley. Like, concave up is always going to be looking like that. And as a way of sort of helping you to see and understand that, to say that this is concave up means that the derivatives must be increasing. We'll take a moment and look at these. The derivative here is 0. The derivative here is 1. The derivative is here is 2. Do you see how these derivatives are increasing? Even if I started out over here where this slope is negative 2, and then this one is negative 1, and then this one is 0, these derivatives, these dy dx, are increasing. I know it may be weird to say that we're increasing from negative 2 to negative 1 because it looks like it's getting less steep. It's not about steepness, it's about the derivative. This slope was negative 2. Negative 1 is bigger. 0 is bigger. 1 is bigger. 2 is bigger. When we say that the second derivative is positive, it means that the derivative is increasing, and that means we say that the function is smiley, is concave up. We can make very, very, very similar statements now about this being negative. If the second derivative of y is negative, it means that the thing that we took the derivative of, in other words, the first derivative, because remember the second derivative is the derivative of the derivative. Sorry, I'm saying derivative like 100 times here. If the second derivative is negative, it means that the first derivative is decreasing compared to x. And remember, the second derivative being negative is sort of the definition, is an understanding that we have of the function being concave down. Remember that concave down means that you have like a sad face graph, or you have half of a sad face graph. And I can make the same argument here, right? If this slope over here is a slope of 3, then it goes down to 2, then it goes down to 1, then it decreases to 0, it decreases to negative 1, it decreases to negative 2, it decreases to negative 3. Do you see how as x increases, as I go along this graph, my dy dx are decreasing? That's what all of this stuff means. The derivatives being decreasing means the second derivative is negative, means the function is concave down. Those are all things that sort of have equivalent meaning to one another. Now I have one final example for us. I'd like us to consider this function, and I've got these 3 questions about the first derivative and the second derivative, and then about a little sketch that we're going to try and do. And so I would highly recommend that, especially for this last one, that you pause the video, try this on your own, and then we'll see where we are. So for part A, it says compute f prime of 1. Okay. So in order to compute f prime of 1, I'm going to need to do f prime of x. So the derivative of this thing, this is going to be a product rule that has a chain rule built into it. So I take the derivative of x squared and leave the e to the negative x alone. And then this time I leave the x squared alone and I do the derivative of e to the negative x, which is e to the negative x, times negative 1, times the derivative of that thing that was inside. I'd like to clean this up a little bit before I do anything more with it. This thing is 2x e to the negative x minus x squared e to the negative x. Cool. So now when I do f prime of 1, just like they asked for, f prime of 1 means 2e to the negative 1 minus 1e to the negative 1. Oh, well great. So 2 of them minus 1 of them. This is just e to the negative 1, which is 1 over e. Now, this question goes on and says, what does this tell you about the behavior of f? We just found that the derivative is positive. What does that tell you about the behavior of f? Hopefully you recognize that because the derivative is positive, the original function must be increasing there. Now, notice that when I wrote this, I tried not to use the word it. I didn't say because it's positive, it is increasing. I said because f prime, because the derivative is positive, the function is increasing. You really, really, really want to make sure that you're precise when you write these things. Now part B asks us to compute f double prime of 1. So to do that, I'm going to need to take the derivative of this. Now, there's going to be a lot of symbols here because I have 2 different parts and each of them requires a product rule and a chain rule. This isn't hard, but we want to make sure that we're careful. So the derivative of 2x is 2, leave this alone, plus 2x, and the derivative of this is e to the negative x times negative 1. Okay? And then over here, I'm going to leave my negative x squared alone. I'm going to take the derivative of that negative x squared and get negative 2x, and I'm going to leave that alone. Okay, gotcha, there we go. And now I'm going to leave this alone and do the derivative of e to the negative x. So that's e to the negative x times negative 1. Now this is a mess. I definitely want to clean this up before I try and do anything. F double prime is going to be 2e to the negative x. This whole thing is negative 2x e to the negative x. Oh, this is actually another negative 2x e to the negative x. And this over here is plus x squared e to the negative x. Now, there's a couple of things that I'm noticing here. One of them is that these 2 things are both the same, right? So since those 2 things are both the same, I'm going to combine them, right? So I can make this 2e to the negative x minus 4x e to the negative x plus x squared e to the negative x. The other thing I noticed is these all have an e to the negative x in them. I could factor that out, and that way I would just have 2 minus 4x plus x squared. Ooh, okay. So there it is. This is my second derivative. Now they wanted me to find specifically f double prime of 1. Okay. F double prime of 1, if I plugged in 1 to this thing, I would get e to the negative 1, that's just 1 over e, times 2 minus 4 plus 1. So that's just negative e to the negative 1. In other words, negative 1 over e. Now the question said, what does that tell us about the behavior of f prime of x and f of x? And so, if you followed me on this one, you might pause the video and think for a moment. We just found that the second derivative is negative. What does that tell you about the derivative, and what does that tell you about the original function? Hopefully you remember from what we had just talked about here that there's a separate statement that we can make for each of these. So we could write or we could say something like, because the second derivative is negative at 1, we know that the derivative is decreasing and the function is concave down at x equals 1. Now the very last thing is I asked us to compute f of 1 and then sketch roughly what f of x looks like at x equals 1. So if I take all of this information and put it together, right? If I take all of this information, we knew that, let's see what we have here, right? We knew that the function was increasing at 1. We knew that the function was concave down at 1. And we know from part C, we know that f of 1 would be 1 e to the negative 1. Because remember, our function was, it was f of x is x squared e to the negative x. So if I plugged 1 into that, I'd get this. So that means I've got this point at 1 comma 1 over e. So if I were to graph this thing, over 1, up 1 over e would be like here or something. The function is supposed to be increasing, but it's supposed to be concave down. So it's supposed to be like a sad face, but it's only supposed to be the increasing part of a sad face. So what this kind of tells us is that in this region, this graph is supposed to be looking something like this. This is our sense of what this graph is going to be looking like in this region. The function will be increasing, but it will still be sad. It will still be concave down. Hopefully this all made sense. I hope that this review has really brought back to your mind a lot of the things that you forgot, and that as we practice that in the assignment today, you'll solidify some of those things before we move forward. As always, if you have any questions, please reach out and ask them, and I wish you best of luck as you work through this practice.